Hi everybody. Today's video is going to be on section 6.5, the matrix of a linear transformation. So we're going to be translating a lot of previous work into a brand new language, okay? Or I should say a new perspective. So earlier, when T was a transformation from Rn to Rm, remember I'm going to be using LT for linear transformation throughout this section, okay? So when T was a linear transformation from Rn to Rm, we had associated a matrix A and called it the transformation matrix of T. In fact, T of V, or I should say T of X, ended up just being A times X, right? And you can do this whenever you have transformation from Rn to Rm. And recall also that A is an M by N matrix. So, question, is it possible to do this with any transformation? So, is this possible to do with any transformation T from V to W? And when I say any, I really do mean any transformation where V and W are not even Rn or Rm. Is it possible to still write this as a matrix? The answer is yes. And that's what we're going to learn how to do in this section. So first, I need to remind you of a definition that we learned. Recall that if B is an ordered basis, for a vector space V, then we had this terminology. Remember, we wrote it this way, and this guy is the component vector of B relative to B. Oh, sorry, the component vector of V relative to B. That's what I meant to write. V relative to B. So this is terminology that we learned in the previous chapter, chapter 4, right? This was from chapter 4. I believe it was section 4.7. Let me just make sure really quick. I'm remembering off the top of my head here. Yes. Yes, it was section 4.7, okay? So, keeping that in mind, we can now define what we mean for the matrix of a transformation. So, let's let V and W be vector spaces. With B, which is going to be V1 to Vn, be an ordered basis for V, and C, which is W1 to Wm, an ordered basis for W. And let's let T going from V to W be a linear transformation. We have something called the matrix representation of T relative to the bases B and C. So I'm going to underline what we're defining here. The matrix representation of T relative to the bases B and C is as follows. So first of all, you notate it this way. You put the transformation name T and then the two bases there, B and C, like that. And what this is it's an M by N matrix, okay? And I'll put that in a second. Each column is going to be the component vector of the transformation of each vector in the basis B relative to the basis C. Okay, I want you to notice something. This is an M by N matrix, okay? Again, each column you get by just applying the transformation to, what is V1? Remember, V1 is, the V's are the basis elements or the basis vectors for basis B. And so what we do is we just apply the transformation to all of the vectors in the basis B, and then write each one relative to basis C and put that as columns in your matrix. And that's going to be an M by N matrix. Okay, so you might need to chew on this definition a little bit, but I'm going to continue. If V is equal to W and B is equal to C, we refer to T, B to B as the matrix representation of T relative to the basis B. Okay, so that's just in the special case that you have a transformation from a vector space to itself and the basis does not change. Let me just fill this, make this B a little clearer here, okay? Now, this idea may seem new to you. It is new to you in general, but if we make some special cases here, you've seen this idea before. So let me make a few remarks here. First, remark 1. If V is Rn and W is Rm, with the standard bases B and C respectively, then the transformation relative to bases B and C is the same as the matrix of the transformation T that you guys learned about in 6.1. So in 6.1, you guys found the matrix of a transformation when it was going from Rm to Rn. So the point is that if the bases are standard and you're dealing with Rm and Rn, then it's the exact same matrix that you guys were finding before. Now, remark number 2. If your two vector spaces are the same and T of V is equal to V for all V, in other words, that means that T is the identity map or the identity transformation. Then T from B to C is really just the change of basis matrix from B to C. And remember this guy we learned about in section 4.7. Right? Because the idea is if you want to change basis, you're not actually changing the vector, you're just changing how you're referring to it. So because of that, you can think of it as the identity transformation, the transformation that doesn't change the vector at all. You're just changing what basis you're looking at it under. Okay? Sort of changing just how you identify it. Okay, let's do an example here where we look for this matrix, okay? So example. Let's let T be a transformation from P1R to P2R. And let this guy be the linear transformation defined by T of A plus BX is equal to 2A minus 3B. You know what? Let me write this on the next line. I'm going to run out of space here. T of, I got to tell you what it does to any polynomial. It's going to be 2A minus 3B plus B minus 5A x plus A minus B, or sorry, A plus B x squared. Okay, so this is our transformation. Part A, I want us to find the matrix representation of the transformation relative to bases B and C, where B is equal to 1x and C is equal to 1x x squared. are the standard bases. These are just the standard bases, right? So this is going to be an easy, part A is going to be pretty easy compared to part B, where we're going to choose bases that are not standard, okay? But when you have standard bases, this is not too difficult to do. Okay, so how do we do this? Remember the definition. We just need to find T of all these things. So T of V1 and V2, which are the vectors in B, relative to basis C, okay? So again, what we're doing is we need to find T of 1 relative to C, and then T of X. Now hold on, did I call it? I forgot. You know what? Let me use bracket notation because I used it before and I don't want to confuse you guys. So this is going to be T of 1 relative to C, and then T of X relative to C. Again, why is that? Because this is my V1 and this is my V2. So remember, I've got to apply the transformation to both of those and then see what they are relative to basis C. Okay. So to do that, I need to find T of 1 first. So let's do T of 1 here. Remember, this is the same as T of 1 plus 0x, right? In other words, we're talking about the polynomial where A is 1 and B is 0 up there. Okay, so if I plug it into the map, I actually get 2 minus 5x plus x squared, which means, and that's easy to write relative to C, right? Because C is just the standard basis right here, right? C is the standard basis. So relative to that basis, this means that T of 1 relative to C is just the column vector 2, negative 5, 1. So we already know this is going to be 2, negative 5, 1 up here. Now for the second column, I need to figure out what T of X is. Remember, T of X is the same as T of 0 plus 1x, right? In other words, A is 0, B is 1. I actually end up with negative 3 plus x squared by plugging into the transformation formula, which means that T of X relative to C, again, that's easy because C is the standard basis. We get negative 3, 1, 1. And so putting those here, negative 3, 1, 1. So when you write an answer like this, you have to ask yourself if the answer makes sense. Remember, guys, coming back up here, we know the dimension of this guy. This guy has dimension 2, and this guy has dimension 3. So we know that the matrix of the transformation should be a 3 by 2 matrix, and it is. So it works. Or I should say it makes sense, right? Checks out. Okay. Now we're going to do a more difficult part. We're going to do the same thing again, except the bases are not going to be standard. Okay, so this is just a part B of the same problem. We're using the same transformation as before, so we're going to find T relative to bases B and C for the bases B, which is 1, 5 plus x, and C, which is going to be 1, 1 plus x, and then 1 plus x squared. Okay. This is going to be a lot trickier, okay? So bear with me here. We're going to work this out. We need to, again, this is V1, remember, and this is V2. So that's what I'm going to need to plug into my transformation. And I need to see what I get relative to this other basis. That's going to be the tricky part, okay? So again, what we're doing is we need to figure out this. And remember, this is going to be the matrix that we get by getting T of 1 relative to C, comma, and then T of 5 plus X relative to C. It should again be a 3x2 matrix, okay? Because we're still going from a 2-dimensional space to a 3-dimensional space. It's just going to be a different matrix than we got before, okay? So let's start by trying to find T of 1 relative to C. So let's start by doing T of 1. Remember, we already did T of 1 previously. If you plug it in, you get this. However, figuring out what T of 1 relative to C is another story, okay? We need to figure out what this is as a linear combination of these C vectors. We can only do that by solving a linear system, okay? So how does it go? We're going to find C1, C2, C3 such that C1 times the first vector plus C2 times the second vector plus C3 times the third vector is equal to 2 minus 5x plus x squared. We know we can solve this by equating coefficients from the left and the right and setting up a matrix, right? Using, you know, what do you call it? Putting it in row echelon form, right? And solving the system that way. Okay, so what do we end up with? We end up with 1, 0, 0, 1, 1, 0, 1, 0, 1, and then we have 2, negative 5, 1. So if we solve this system, this will give us exactly the constants that add up to that polynomial. So we're going to put this in row echelon form. I need to add negative 1, row 2 to row 3, and that'll do it. So if I do that, I end up with 1, 0, 0, 0, 1, 0, 1, 0, 1. And I end up with 7, negative 5, 1. So if I solve this system, I get C3 equals 1, C2 equals negative 5, and C1 equals 7 minus C3, which is 7 minus 1, which is 6. So bringing what I got back up here, this means that 6, negative 5, 1 is exactly T of 1 relative to C, which means that's going to be the first column of my answer. 6, negative 5, 1. Now I need to find the second column. It's going to be the exact same thing, except we're now going to do T of the second basis vector in B, which was 5 plus x. Okay. So if you plug that into the transformation equation at the beginning of the problem, we end up with 7 minus 24x plus 6x squared. So we need to find T of 5 plus x relative to C. Okay, we don't know what this is yet, so we're going to need to figure that out. Again, we're going to do this using a system. We need to find C1, C2, C3, such that C1 times 1 plus C2 times 1 plus x plus C3 times 1 plus x squared is equal to 7 minus 24x plus 6x squared. So setting up our augmented matrix, this first part is the same, but now we're going to put 7, negative 24, 6 there. So we're going to add, again, it's actually the same exact step, right? We're going to add negative 1 row 2's to row 3. And if we do this, we end up with 1, 0, 0, 0, 1, 0, 1, 0, 1. And then this is going to be 31, negative 24, 6. What does this mean? So C3 is 6, C2 is negative 24, and C1 is 31 minus C3, which is 6, which is 25. So that means my component vector relative to C for this element is 25, negative 24, and 6. So coming back to the very beginning, we can now write our final answer here. Put that as my second column. And we end up with 25, 6, put that in, and this is our answer, right? This is T, this is the transformation, the matrix representation of T relative to basis B and C. So why is this important? Why do we care about this? And how do we actually use a matrix like this in practice? Okay, well, this does exactly what you would expect it to do, okay? The way that this works is given by the following theorem. The following theorem is going to tell us exactly what this guy can be calculated to do, and I'll illustrate it using a picture. So first, let's let V and W be vector spaces. With bases B and C respectively. And let's let T from V to W be a linear transformation. For all V in V, if you take T from B to C and apply it, this is matrix multiplication, by the way, right? If you apply it to the component vector of V relative to B, this will give you the component vector of T of V relative to C. This should look very familiar to you, okay? This is sort of like at the beginning of the section. This is like that, right? In other words, what we're saying is instead of applying the transformation to something and finding the component vector relative to C, you can first find the component vector relative to B of the vector and apply the transformation by just multiplying the matrix that we just found. Okay? So if we were to draw a picture of this, which I like doing because it helps us visualize what we're looking at here. So let's call this guy over here V, and let's call this guy over here W, okay? And so we've got this guy, and this is going to be V relative to B. And over here we have T of V relative to C. What we're saying is we can get from here to here by just multiplying on the left by T, this matrix that we just learned about. And by the way, that's no different. It's no different, guys, from calling this V and calling this guy T of V, and then we just get that way using T. Okay, in other words, it's the same concept. It's just realizing a couple of things here. First of all, every single vector needs a name, and we always name it relative to a basis. So what we're saying is, if you want to treat it as just the basis coefficients, right, the component vector, then we can apply the same transformation by multiplying it on the left by the corresponding matrix. Okay? So I hope that visual helped. So let me write down sort of something we should keep in mind here. So writing a transformation in matrix form is extremely powerful as this allows us to apply any transformation using matrix multiplication. Okay. So it's a neat perspective. So as a new example, I want to show something. So let me just say in this next example, we will demonstrate that if you're starting with only the matrix representation of a transformation, we can use it to recover the transformation formula at any time. Okay, so I want us to sort of look at the last example. So in part B of the last example, remember we found this. Now we're going to work backwards. In other words, if you start with this, how would you use this to figure out? So use this to determine the transformation formula for t of a plus bx. Remember, the problem started with us being given that, right? If we go back to that last example, what I'm talking about is this guy right here, this formula right here. How can we get back to that formula if we just have the matrix representation of the transformation relative to some bases, okay? So that's going to be our answer that we're trying to get to for this next example. So we're going to do this by figuring out everything in reverse, okay? So we start, so to find t of a plus bx, the idea is going to be to use that last theorem we wrote down, okay? So all we need to do is recall the following. We know that if we take t from b to c, that's the matrix right up there, and if we multiply it by a plus bx relative to b, let me write it with the brackets again, sorry. A plus bx relative to b, this is going to give us t of a plus bx relative to c. So our first step, so step one is going to be to find a plus bx relative to b, and step two will be to actually multiply them. So step one is to find a plus bx relative to b. How do we do that? Well, again, we're going to set up a system, right? We know that we want to find, well, let me write down the next line here. We want to find C1, C2, such that C1 times, again, I'm looking up now the basis B for this example, right? Remember, basis B was 1 comma 5 plus x. So C1 times 1 plus C2 times 5 plus x. And we want this to equal a plus bx. Okay, now yes, the answer here is going to be in terms of a and b, but that's okay. So we have 1, 0, 5, 1, and then this is going to be a, b. And so we just need to put this in row echelon, and actually we don't even need to do that. The system is essentially already solved, right? Because C2 has to be b, and then C1 has to be a minus 5b. So we literally just found what C1 and C2 are, and so that gives us our exact a plus bx relative to b. So this means that a plus bx relative to b is the 2x1 matrix a minus 5b and b. Step 2, multiply. Right, we're going to multiply t from b to c times a plus bx relative to b. So this is going to equal the two matrices, right? We have the matrix that we were given at the beginning. And we need to multiply this by a minus 5b and b, right? this is a 3 by 2 times a 2 by 1. The answer will be a 3 by 1. And if you work through the multiplication here, you will end up with the following. 6a minus 5b, negative 5a plus b, and a plus b. So, now what? Remember, what we just found, this guy is not our coefficients, but it is t of a plus bx relative to c. So now we just need to multiply each of those coefficients by the c vectors. Okay, so that means step 3 is going to be to simplify. Right? So we know this is going to be 6a minus 5b times the first basis vector, which was 1, plus negative 5a plus b times the second basis vector, which is 1 plus x, plus, and then a plus b times the third basis vector, which is 1 plus x squared. So if you do this algebra, collect the like terms, what you end up with is two a minus 3b plus b minus 5ax plus a plus b x squared, which is exactly what we were supposed to end up with, right? That's how the transformation was defined at the beginning of part B. Sorry, at the beginning of the last example. So, understanding this section, we really need to make sure we understand section 4.7, right? Because a lot of what we're doing here relies on understanding 4.7. Okay, so how does the change of basis matrix factor into all of this? We have a really nice theorem. Let V be a vector space with ordered bases B and C. Also, let T be a linear transformation from a vector space to itself. Then the following is true. So reading from right to left, if you apply the change of basis matrix from C to B, then the transformation matrix from relative to basis B to itself, and then the change of basis matrix from B to C, that's the same as doing the transformation matrix relative to basis C. Now, this looks more complicated than it really is. So what I want to do is I want to give you, it's not really a proof, but this is a picture proof. I'll call it a picture proof, even though this is not a real proof, because it's going to be a visual of the whole thing, which will help you understand what's going on here, okay? So, same as before, here's V. V relative to C. And if I apply, let's start with, so let's apply all of these one at a time, okay? So we're going to work with this side here. So if you were to apply if you were to multiply this entire thing on the left by this, what happens? First, you have a change of basis matrix from C to B. In other words, that guy is going to take this guy and write it as V relative to B, right? So that's what, let me write it in red. That's what this guy does. Change of basis matrix from C to B. Then, if we apply this next guy, this takes us to T of V relative to B. That is a different guy here, right? And then finally, if I apply the change of basis matrix from B to C, I end up with this guy relative to C. Let me actually put the dot above here. And so applying all three of these things from right to left gets you from this dot to this dot, right? Now, the whole point is we could have gone there directly if we had just applied this guy instead. Instead of changing the basis, then doing the transformation, then changing the basis back, we could have just applied the transformation directly. And that's exactly what the right side of this equal sign is. Now, it's important to note that the only actual thing we're talking about here are two dots. There's only two elements we're talking about, right? One of them is V and the other is T of V. So everything you see below, like these things, are just different names for it. These two are just different names for that guy, but we really are just talking about one vector and a transformation that brings you from one to the other. And all these change of basis matrices do is allow you to name something in terms of a different basis, right? It's like calling a person by their last name instead of their first name. It's a different name to refer to the same thing. Okay, so you can probably imagine these are not the only connections to previous things that we've done. And so the last thing we're going to do is we're going to translate some previous ideas into this new language. Let me write that specifically here. We now translate previous linear transformation ideas into our new language. Okay. So first, I need some notation. So let's let U, V, and W be vector spaces with bases A, B, C, respectively. And let's let T1 go from U to W, sorry, not U to W, U to V, and T2 go from V to W be linear transformations. Then the following is true. If you compose those guys, we know that T2, T1 is going to be the same as applying T1 and applying T2. It turns out that when you multiply the matrices, it's the same thing. So in other words, if you want to find this, T2, T1, relative to bases A and C, all you have to do is multiply T2 from B to C times T1 from A to B. Another way to say this is a composition of two. Okay, hold on. So let me write it this way. The matrix representation of a composition of two transformations can be obtained by multiplying their matrix representations. Okay, so this is the first fact, okay? So I'm going to call this fact 1. Now let me use another, let me use blue. This is fact 1. Okay, what about fact 2? This time, let's let T going from V to W be a linear transformation. And let B and C be ordered bases for V and W, respectively. All of the following are true. What's the connection between the kernel? A lot of you say that the kernel is the null space. Now be careful. Not every transformation is a matrix, but now we know that it actually is as long as you do it this way. So what we've learned then, what happens to be true, is that a vector is in the kernel if and only if its component vector relative to the basis B is in the null space of the transformation matrix from B to C. So all the stuff that we did with the transformation matrix before, we can now do with the new one as long as we make sure we look at it carefully, okay? So another thing that we know, W is in the range of T if and only if the component vector of W relative to C is in the column space of T from B to C. So we could still use null space and column space to figure out the kernel and the range as long as we look at the correct matrix here, right? We have to find the matrix relative to those bases that we're talking about. So what's cool is you could figure out immediately if a map is 1-to-1. So T is, remember before we said T was 1-to-1 if the kernel was 0. Of course, that's true for any linear transformation, but when we're dealing with a matrix of the transformation, then this is true if and only if the null space of T from B to C is just equal to the 0 vector. So the null space of the matrix of the transformation, if that's just the column of zeros, then you know that it's going to be 1-to-1. Also, T is onto if and only if the column space of T from B to C is equal to all of Rn. What is n in this case? N is going to be the dimension of W, where the dimension of W is n. Okay? In other words, all linear combinations, you have to get all possible linear combinations, right, in order for the range, because then that would give you every single vector in the space. Okay, so last fact, fact 3. I know that each fact has a bunch of sub-facts there, but I think this is the best way to write this. These are all kind of related here, okay? Okay, so this time we're going to let T be a transformation from V to W. So let this guy be a linear transformation of vector spaces. With bases B and C respectively. But here's the catch for this part. Suppose the dimension of V is equal to the dimension of W. So suppose we're going from n dimensions to n dimensions. So they're both going to be n. Notice, what does this mean? This means that our transformation matrix from, it doesn't really matter, right? Bases B to C, this means that this guy is an n by n matrix. So what are the facts then? The facts are T is 1-to-1 and onto if and only if the matrix of the transformation is invertible. That's a very cool fact. So how can we find the inverse? So that's going to be our last fact here. If t from b to c is invertible, then the inverse of that matrix representation is actually equal to the inverse transformation relative to C to B. This is a really cool fact, okay? I want to draw a picture of this so that we understand what's going on here, okay? So, here's V. Here's W. And we know that if we have a V here, if you apply T to it, you go to T of V, right? And if you apply T inverse to that, you come back. Oops, let me use same color here. But now let's just go ahead and name it relative to a basis, right? When you name it relative to a basis, then it becomes matrix multiplication, right? So if we call this guy V relative to B, and then that means all we have to do is apply T from B to C, then that gives us T of V relative to C. So it stands to reason that you can come back using the T inverse matrix relative to or from C to B. Okay, so really what I've just shown you again is a picture proof of why this works, because this means we know that if T from B to C times V of B, or V sub B, we know that this is equal to this. Oops, let me center this again. We know that this is equal to this. Hold on, let me make sure I do this correctly. So we know that's going to bring us there, and so yeah, if I apply the inverse transformation now, it's going to bring us back the other way, right? So applying it on the left by T, there you go. Okay, so if I were to apply this on the left by T inverse C to B, then this is going to be this. That's what the picture shows, right? That you go back and forth, okay? T from B to C brings it over there, and then T inverse C to B brings it back, right? And so what does that mean? That means that if you take the inverse map, you see how we have t from b to c inverse. So I hope that this picture makes sense. One more thing that I want us to think about here. One more thing that I want us to think about here is the fact that this actually means, and this is probably something you've never made the connection with before. It's a kind of a big idea that every invertible n by n matrix is actually an isomorphism, or actually, let me write this more specifically, is actually a matrix representation of an isomorphism of n-dimensional vector spaces. Really cool idea, right? It could actually be any n-dimensional vector spaces because it tells you what it does relative to any basis that you want. All right, everybody. So I hope that was clear. I know that we said a lot in this lesson. So, please make sure you look over it. Quite a lot of details here, but if you work through all the little details that I worked out and you do some examples, it should become clear. All right, everybody, that's it for this. Thank you so much for watching.